Okay, so the reason we uh, set things up like this so that we talk about events and sample spaces and things like that, experiments, is because we want to be able to figure out how to calculate probabilities of events. So for example, what's the probability of getting an odd number? Everybody knows that, but what's the probability of getting a number less than 4? And so on. So we want to figure out how to calculate probabilities. So the first thing we did was talk about what we mean by an event, because when we talk about probabilities, we're always talking about the probability of some event. So we tried to make clear what we mean by that word event before we talk about how to calculate the probability of it. So the next thing we're going to try and make clear is what we mean by probability. Now, if we ask, well, what do you mean by when somebody says the probability of getting heads when you toss a coin is 1/2, you say, well, what do you mean by that? What does that mean? And people will say something like, well, it means that the chances are 1/2, but that doesn't really make it any clearer, right? Say the probability is 1/2, the chances are 1/2 doesn't really, it's not any better. It's the same answer as the question was. So it's a little bit hard to say what that means, even though we all agree that the probability is 1/2. But when you try and figure out what does it mean to say that it's 1/2, you just come up with something like, well, it means the chances are 1/2. For example, it doesn't mean that if I toss a coin 10 times that I'm going to absolutely get 5 heads, right? That's not necessarily true. So it doesn't really mean that. So it's a little bit hard to figure out what it actually means. So they start out by saying the probability of an event is a measure of our belief that the event will occur. So it's some kind of measure of our belief that an event will occur. Okay, that's not necessarily much better. So we'll take it another step. So let's think about let's first define something called the relative frequency. So the relative frequency is simple. If I toss a coin 100 times and I get 60 heads, we say the frequency of heads is 60, not the relative frequency. The frequency, if I just write this, just the frequency is 60. In other words, it just occurred 60 times. The relative frequency is 60 out of 100. So it's 0.6, right? 60 over 100. Okay? So they say the relative frequency is the frequency over the number of times that you did the experiment. So what do I mean by the number of times you did the experiment? Well, I'm saying if you toss the coin 100 times, we can say that we did the experiment of tossing a coin. We did it 100 times. So that's n is 100. And the frequency means the frequency of the event that you're interested in. In this case, I said heads. I was interested in heads. So it's 60 over 100. Okay, let's say I rolled a die 10 times, and I could talk about the relative frequency of the number of times I got a 3. So how many times did the 3 occur? So suppose I got a 3 2 times. So the frequency would be 2. That is, I got a 3 twice. So the frequency would be 2. And the relative frequency would be what? Well, I rolled it 10 times, and twice I got a 3. So it's 2 out of 10. So that would be the relative frequency, 2 out of 10. 2 times out of 10 I got whatever I was talking about. In this case, I was talking about getting 3 dots. So why are we interested in relative frequency? Remember, our question is, we're trying to understand what probability means. So let's think about that question again. We said the probability of heads is 1/2. Again, what does that mean? What does it mean that the probability of heads is 1/2? And again, I said it doesn't mean that if I toss a coin 10 times, I'm necessarily going to get exactly half of the times are going to be heads. It doesn't mean that I'm necessarily going to get 5 heads. I might get 4 heads, or I might get 2 heads, or I might get no heads. So what does it mean? Well, if I toss a coin 10 times, I'm not necessarily going to get 5 heads. So but what is the, okay, so we can talk about the relative frequency of the number of heads though. So suppose I got 4 heads, then what would the relative frequency be? It would be 4 over 10. Okay, suppose I toss the coin 100 times. I'm not necessarily going to get exactly 50 heads, right? Maybe I'll get 45 heads. Okay, then what would the relative frequency be? 45 over 100. In other words, 0.45. If I toss the coin 1,000 times, again, I'm not necessarily going to get 500 heads, but I might get like 475 heads or something like that. Anything could be possible, but anything between 0 and 1,000. But let's say I got 475. That would be what? 475 over 1,000. Now consider these numbers that I've just been talking about. First I said 4 over 10. That's so here are the 3 cases. So 4 out of 10, 45 out of 100, 475 over 1,000. So this is what? 0.4. This is 0.45. This is 0.475, right? So we're talking about the frequency over n, which is called the relative frequency. And if I toss it 10 times, I might have gotten 0.4. If I toss it 100 times, I might have gotten 0.45. If I toss it 1,000 times, I might have gotten 0.475. So I think it's fair to say that what we mean by the probability, when we say the probability is a half, what we mean is that if we toss it 10 times, 100 times, 1,000 times, 10,000 times, and so on, we expect that these numbers are going to be getting closer and closer to 1/2. That's kind of what we mean by saying that the probability is 1/2. We mean, for example, suppose these numbers didn't get closer and closer to 1/2. Right now it looks like they are getting closer and closer to 1/2. But suppose they seem to be getting closer and closer to like 0.40. Like this time it was 0.40, then it was 0.45, then it was 0.475, but next time for 10,000 it was like 0.45, and then it was 0.41, and they just seem to, and as I do more and more tosses, it seems to be getting closer and closer to this number. Then I might say, oh, I don't think this is a fair coin. There's something wrong with this coin. It's not balanced properly. Because the probability, it seems to me, is not a half, but 0.4. In other words, what I'm saying is I kind of get my idea of what the probability is by what happens as I toss more and more coins. Right? You would even throw out your idea that the probability is a half if this process tended towards 0.4 instead of 1/2. So that's an argument to say that what we mean by probability is what happens as this process proceeds. And this is a notation for that. As we were just looking at the frequency over n for when n was 10, and then 100, and then 1,000, and then we said, okay, how about if we did it 10,000 times, and 100,000 times, and 1,000,000 times, and 10 million times, and 100 million times, and what we're doing is we're just letting n get bigger and bigger and bigger. And that's what this means. This means just let n get bigger and bigger and bigger and see what happens. And so, if as we let n get bigger and bigger and bigger, this thing looks like it's getting closer and closer to a half, then we're going to say the probability is 1/2. Probability of our event, and our event in this case is getting heads, right? Just getting heads. So we'll say the probability of that event is 1/2. Okay? So this is actually what we're going to use for our definition of what we mean by probability. Remember we said it's hard to say what we mean by probability, but this is a kind of mathematical construction that you may or may not have studied, but it's been studied a lot anyway. And so this kind of makes sense mathematically. So that's what we're going to say is the meaning of the probability of some event A. So probability is this. So it certainly, it has in it this thing, which we've been talking about, called the relative frequency. So probability is kind of like a relative frequency. And so if it's like a relative frequency, it's going to have properties that relative frequencies have. Now relative frequencies, obviously this number, the top number, let me see if I can just get that part. Oh, I can't seem to just get that part. I'll start from here. No, can't do it. Oh well. Anyway, frequency is never going to be bigger than n, right? Because, like you toss a coin 100 times, you're not going to get more than 100 heads. So frequency is never bigger than n. That means this is always smaller, the top is always smaller than the bottom. That means the whole thing is less than 1, always. Right? So relative frequency is always less than 1, less than or equal to 1. So probability is going to be the same thing, always less than or equal to 1. And on the other hand, this top part is never going to be less than 0, not going to be a negative number. You don't say, I got negative 3 heads. That doesn't mean anything, doesn't make any sense. Right? So it's always going to be at 0 or more. So if you have 0 on the top, then this is going to be 0. So in other words, this number is never going to be negative. This fraction is never going to be negative. So probabilities will never be negative. So we just said that probabilities are always greater than or equal to 0 and less than or equal to 1. So I can't really write less than or equal to very well, so I just wrote it like this and this. I guess what, greater than, whatever. So I'm saying that probability of A is always between 0 and 1. Greater than or equal to 0 and less than or equal to 1. So what does it mean if the probability is very close to 1? It means that it's that this event A is very, very likely to occur. And what does it mean if it's very close to 0? It means that this event A is very unlikely to occur. So they say since P of A behaves like a relative frequency, it is basically a kind of relative, or it's close to the idea of a relative frequency. P of A must be a proportion, a fraction, lying between 0 and 1. P of A equals 0 if the event never occurs. So if the probability is actually 0, then it means that it will never happen. So the probability, what's an example of that? The probability that I get both heads and tails on a single toss of a coin, that's never going to happen. So I guess I could say the probability of that is 0. The probability equals 1 if the event always occurs. Okay. The closer P of A is to 1, the more likely it is that A will occur. Okay, here are two more requirements for what we mean for probabilities. And we're talking only about this probabilities for simple events. So I can talk about the probability of getting an even number, but that's not a simple event, right? An even number is not what we call a simple event. The simple events are like getting a 1 or getting a 2 or getting, those are the simple events. So let's make some observations about probabilities for simple events. First of all, like we already said, each probability must lie between 0 and 1. Right, we already said that. And one more thing, and that is the sum of the probabilities for all the simple events in S equals 1. So like if we go back to the idea of tossing a die. Okay, what is the sample space? Okay, this is the sample space. And the simple events are getting a 1, getting a 2, except each one of them separately. So if I take the probability of getting a 1, and the probability of getting a 2, and the probability of getting a 3, and so on, if I add up all those probabilities, what do I have to get? Those are the probabilities of each possible case. So they have to add up to 1, 100%. Okay? Now that's not quite saying that the probability of getting a 1 is 1/6, and the probability of getting a 2 is 1/6, and the probability of getting a 3 is 1. That's the normal case, though. we normally say that the probability of getting a 1 is 1/6, the probability of getting a 2 is 1/6, probability of getting a 3 is 1/6, probability of getting a 4. Right there, all the probabilities, each would be 1/6. And so when we add them up, we get 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6, which is 6/6, which is 1, which is what we said, the probability and when you add up all the probabilities of all the simple events, you should get 1. But I'm not necessarily saying that they all have to be 1/6. Like you might have an unfair, unbalanced die. Like maybe the 5 turns up more often. Somebody weighted the die somehow, so that 5 turns up more often. So that this one is more likely, so they're not all 1/6. So they'll be different numbers. They won't all be 1/6. They'll have some difference than that from that. But still, when you add up all the probabilities, you still have to get 1, or 100%, up to 1. But still, when you add them all up, it's logically necessary that they have to add up to 1. So this says the sum of the probabilities for all simple events in S equals 1. So that's important. That will help us when we do calculations. When it is possible to write down the simple events associated with an experiment to determine their respective probabilities, we can find the probability of an event by summing event A by summing the probabilities. Okay, so sometimes it's not possible to write down all the simple events. If it's possible that you have like an infinite sample space, so you can't do that. So maybe we'll see an example of that. But anyway, normally we can write them down. So let's take this one. Toss 2 fair coins. We haven't talked about tossing 2 coins. And record the outcome. Find the probability of observing exactly 1 head. Now here, first thing you want to do is figure out the sample space, and maybe we should use a tree diagram to do that, like we did before. So here, let's try it again. So if we have an origin here, we just arbitrarily put a dot here, and then we talk about the first toss of the coin, or first coin, and we get head and tail as the 2 possibilities. So we have heads and tails, and then if you get heads on the first coin, we write for the second coin, you can get heads or tails. So we have an outcome heads and heads, which we write HH. We get an outcome heads and tails, which we write HT. We get an outcome tails and heads, which we write TH and TT. And these are the simple events, and so there's 1, 2, 3, 4 of them. Okay, so the simple events, there's 4 of them. So the sample space consists of those 4 simple events, so it has 4 elements in it. Okay, so the sample space has 4 elements in it, just like before. We had this sample space before. Where is it? Here. There were 8 elements in this. So now we're going to have 4 elements in our sample space. So the first element is going to be HH. It looks like it's 2 elements, but it's not. It's 1 element. It's one possible outcome for the combined experiment of tossing 2 coins. So you can, when you toss 2 coins, you can't just get an H. You have to say what you got for both coins, so you can't just get an H. You can get an HH, you can get an HT, you can get a TH, and here we're making a distinction between this one and this one. What's the distinction? This means that you got heads on the first, and this one means you got tails on the first. So they're different, right? Okay, so there's 4 possibilities, and remember that we just said that they have to add up to 1. That is, the probability of the first simple event, this, plus the probability of this, plus the probability of this, plus the probability of this, they all have to add up to 1. So normally, if we talk about a fair coin, a balanced coin, we're going to say that the probability of this is the same as the probability of this, is the same as the probability of this, is the same as the probability of this. And if they all have to add up to 1, that means that each of them should be 1 over 4. The probability of HH should be 1/4. The probability of HT should be 1/4, and so on. So they say here, to list the simple events in the sample space, you can use a tree diagram. The letters H and T mean that you observed a head or a tail respectively on your particular toss. To assign probabilities to each of the 4 simple events we've just discovered there are 4, you need to remember that the coins are fair. So they said fair up here. So you need to remember that they're fair. Therefore, any of the 4 simple events is as likely as any other. Since the sum of the 4 simple events must be 1, each of them has to be a quarter. The simple events in the sample space are shown in table 4.2, along with the equally likely probabilities. Where's that? Here. Event, first coin H, second coin